Good day, everybody. I'm going to present DREAMS. This is the Dresden AMS facility, which is located at the Ion Beam Center at HZDR. DREAMS is one of two AMS facilities. Which is part within these activities here. The second one is the University of Vienna facility Vera, where Peter is going to give a presentation, I think, in 15-20 minutes from now. Details on DREAMS can also be found, of course, on the web page, and there is more details listed. First of all, if you go to the next slide, I will present just two slides to give some kind of a snapshot what AMS is, what AMS can do, what AMS can measure. This slide here just illustrates that AMS is a method that is used in a wide range of different applications. It's most well known for radiocarbon dating, but it's not only radiocarbon dating. There are many more applications that utilize long-lived radionuclides. That is important. And it's a mass spectrometric technique. So it's a technique that is based on an accelerator and uses mass spectrometric techniques and nuclear techniques to identify single atoms, single radionuclides. This is applied to a wide range of applications as shown here in environmental, geological research, anthropogenic nuclides, techniques, nuclear fusion, nuclear fission, but also in nuclear astrophysics, of course. If we go to the next slide, in general, it's about 20 to 30 radionuclides that are measured with AMS. Most are routinely measured in some dedicated AMS facilities. Some are exotic radionuclides, which are difficult to measure. Because this is single atom counting, the method itself does not depend on the half-life. So it can be as short as some years, even in some exotic applications. It can be days, 14 days, I think, was one of the shortest lived radionuclides, which has been applied in AMS. And on the other hand, it can be as long as some orders of 100 million years. So plutonium-244 would be one example here, which is of interest to nuclear astrophysics, has a half-life of 80 million years. Because we do not measure the decay, but we directly count the atoms. So the method itself does not depend on the half-life. It's a limited number of radionuclides where AMS can be applied, but often it is the case that if it can be used, if AMS can be used, then it's the far most sensitive technique. It's an ultra-sensitive technique because it directly counts the number of atoms like carbon-14 or aluminium-26 or iron-60, etc. So decay counting wouldn't work. If we go to the next slide, besides DREAMS, which offers about 8 radionuclides that are routinely measured here, we are now in the process of setting up an additional facility, a dedicated compact AMS facility, which will come into operation hopefully in 2 years from now. So commissioning is planned for early 2023. It will be a state-of-the-art AMS facility and will offer a number of new and additional radionuclides to be measured. And because this is 2023, so it's just in the middle of the research activities here of this project. So we hope that this facility will also become part of the transnational access activities in the future. The system itself is also built on some new technological developments, which are going to be performed together with the University of Vienna, which has actually pioneered isobaric suppression techniques using laser photo detachment. Possibly Peter will go to add a few more details on this. If we go to the next slide. So if we come back to nuclear astrophysics and AMS, a few topics are listed here where AMS has been used in the past. One is, of course, nuclear reaction studies for simulating nuclear synthesis in stars, so cross-section measurements. Second point would be to search for interstellar material that enters the solar system and eventually becomes deposited on Earth. In particular, one topic is the search for supernova-produced radionuclides. like iron 60, manganese 53, or possibly also plutonium 244. And finally, I have also listed meteorites as another example of nuclear astrophysics applications where AMS can be used. If we go to the next slide, this is one example here. Most of you will know this. This is related to the topic, can we see interstellar signals on Earth? For example, in this case here, it's iron 60. Iron 60 was detected in terrestrial archives in deep sea sediments and deep sea crusts. And what is plotted here is on the horizontal axis is a time period given between 0, this is present, and 10 million years ago. And on the vertical axis, you see some kind of an iron 60 influx. And you see that there are two peaks. One is at about 2 to 3 million years, and there's another one now clearly shown between 6 and 7 million years. What it tells us is that there is a nearby supernova activity to the solar system. There were several supernova explosions during the last few million years. This is based on AMS measurements at the ANU for iron 60. In this case, there were more measurements done in Munich, which has closed, just sad story itself. The age was measured by beryllium 10, and so there are other candidates listed below, so which are also of interest for this kind of studies. Beryllium 10 can be used for age dating of this terrestrial archives. We have used aluminium 26 as a signal from interstellar influx. There would be other candidates like manganese 53. There are developments ongoing in Vienna on hafnium 182. Plutonium 244 is a candidate where we have recently found some indications on this as well. And these nuclides, or part of these nuclides, might become available also with the new system that we hope to commission in about 1.5 to 2 years. Let's go to the next slide. The second topic is, of course, as I mentioned before, nuclear synthesis in the laboratory. This means we study cross-section or nuclear reactions. And because AMS uses long-lived radionuclides, we can first perform a sample activation. And usually this activation is not limited in time because our reaction product of interest that we want to measure by AMS is long-lived, so it will not decay away. The whole process is, of course, a two-step process. We have first sample activation, producing a radionuclide. For AMS, it's a longer-lived radionuclide. And then after the activation, we use accelerator mass spectrometry. Here in this case, as an example, is the Vera laboratories where we then directly count or detect the reaction products, the radionuclides. Okay, let's go to the next slide. This slide here shows a number of nuclear reactions, in this case, neutron-induced reactions. Of course, AMS has been used for charge particle-induced reactions, alpha particles, or proton-induced reactions. Here, this is a list of neutron-induced reactions where the sample activations had been performed in Karlsruhe. And still, Franz Kepler had been active, and we used the same setup for a set of neutron capture reactions. Why I'm showing this comes to the next slide. And the next slide here gives you results, relative results now for the neutron capture reactions at 25 keV max valiant, so which is of interest to nuclear astrophysics. This is relative results AMS versus time of flight data for some of the reactions that we have started where AMS had been used, and it is compared AMS to the neutron time of flight data. And what you see here is that for some reactions, we have a systematic difference of about 10%, which is not understood. This is, for example, one topic which is certainly worth to pursue here also within these activities here. And we want to continue on this neutron capture cross-section measurements, try to understand what is the reason for this systematic difference. AMS is a complementary technique. Data had been produced here not only in one facility, but on different facilities. And it needs quite, I think, some more detailed studies to see what is the reason for this difference. So this brings me to my end. So those who are interested in translational access activities using accelerator mass spectrometry, in particular here in Dresden, they should contact either me, Georg Rubel, or Johannes Lachner. We're happy to provide more details, but you also find some more details on the webpage. Okay, thanks for your attention. I made it in 10 minutes.